Welcome back to Hypothesis Testing Done Right, Part 4 of 14. In Part 3, we built the t-statistic, estimate minus null, over the estimated standard error, and saw why its tails are a little heavier than the normals. Now we put real numbers in. We compute Sam's t, and then we change one thing, the sample size, and watch the verdict flip while the average return stays exactly the same. Let's put numbers in. Say Sam's 252 daily returns have a mean of 8 basis points and a sample standard deviation of 75 basis points. First, the square root of n, the square root of 252 is about 15.87. The estimated standard error is the sample standard deviation divided by that. 75 basis points divided by 15.87, which is roughly 0.0473%. Now the t-statistic is the estimate minus the null, all over that standard error, 8 basis points minus 0 divided by 0.0473%, which comes out to about 1.69. So Sam's average return sits about 1.69 estimated standard errors above 0. That is the single number we will judge against the skeptic's world. Hold on to it. 1.69, because everything from here is just a different way of asking how impressive it really is. Now watch the role of the sample size in that denominator. Suppose Sam had run the rule for only 1 quarter, 63 days, and got the exact same average of 8 basis points with the exact same spread of 75 basis points. The square root of 63 is about 7.94, so the estimated standard error is now 75 basis points divided by that, roughly 0.0945%, twice as large as before, because we have 1 quarter the data and the standard error scales with 1 over the square root of n. The t-statistic is then 8 basis points divided by 0.0945%, about 0.85. That is less than half the t we got from the full year, and it is nowhere near significant. Stop and feel how strange this is. Identical average return, opposite conclusion, purely because of how much data backed it. This is the single most important practical lesson of the standard error. A result is only as convincing as the sample size beneath it. The same 8 basis points can be a discovery or a shrug, and the only thing that changed was n. Is 1.69 far enough to overturn the skeptic? To answer, we need to decide how surprised we must be before we act. To summarize Part 4, plugging in Sam's numbers, an 8 basis point average, a 75 basis point standard deviation, and 252 days, gives an estimated standard error of about 0.0473%, and a t-statistic of about 1.69. Sam's average sits 1.69 standard errors above the skeptic's 0. The punchline is what happens when we shrink the sample. The very same average return, measured over a single quarter instead of a full year, yields a t of only about 0.85. Identical return, opposite verdict. The standard error square root of n is doing all the work, and the lesson is permanent. A finding is only as convincing as the data beneath it. In Part 5, we ask, what would make 1.69 far enough to act on by laying out the 2 distinct ways any test can be wrong, size, and power.